Hello, my name is Ibra.
And I'm Celine.
And so we studied under the mentorship of Angel Gomez in the Hosea Nelson Lab, which primarily focuses on synthetic chemistry.
So before we get started on actually what we did in the lab, I wanted to give a little bit of background about carbocations. And for the past 100 years, chemists has been using carbocations to make simpler molecules into more complex molecules. And the most common type of carbocation is called a trichlorinated carbocation. So if we make sure. So we're talking about a trichlorinated carbocation. So a carbocation is basically a carbon atom that has only 6 electrons in its valence electron shell instead of the usual 8, meaning that it carries a positive charge and it has an empty p orbital. And a trichlorinated carbocation is a carbon atom with a positive charge that is bonded to 3 different things. So 1, 2, 3. And it usually experiences stabilization through resonance and hyperconjugation. Resonance is basically when this molecule S has 2 electrons and it donates its electrons into this bond right here. And this gets turned into a double bond. And the positive charge from the carbon atom moves up into the X molecule. And this stabilizes because delocalizing the positive charge over 2 atoms is lower in energy than concentrating that charge on a single atom. Hyperconjugation is when electrons from its surrounding donate their electrons to help stabilize the carbocation. So in the Nelson lab specifically, we studied the reactivity of dichlorinated carbocations, which is a carbon atom with a positive charge that is bonded to 2 different things. And this is a really special carbocation because they experience less stability from resonance and hyperconjugation. And these carbocations are highly reactive because of its instability, and chemists wants to find what kind of chemistry this type of molecule can do. And in order to isolate these highly reactive non-coordinating carbocations, we have to pair them with weakly coordinating anions. And these weakly coordinating anions act like spectator ions, where it doesn't really do anything and it's weak enough to be a bystander, so it won't attack or bond with the cation when it's sitting there. So one example of a weakly coordinating anion is this one. This one is called carbon.
So some of the reactions that the Nelson lab has made include these 2 reactions. Specifically, the 2 reactions that we use are carbon and psyllium catalysts to activate the aryl fluorides. In the first reaction, an aryl fluoride is activated by using a psyllium catalyst. The catalyst removes the fluoride ion, which creates a carbocation on the aromatic ring. This carbocation then reacts with a hydrocarbon to form a carbon-carbon bond, which is this double bond. The second reaction begins with a vinyl triflate, in which a molecule containing a triflate group, or ODF, the catalyst activates the vinyl triflate by causing the triflate group to leave, forming a vinyl carbocation. And this is basically the catalytic cycle of how the carbon-carbon bond is formed. So the cycle begins with initiation, in which the catalyst reacts with silane to generate psyllium. The psyllium ion then removes the fluoride ion from the aryl fluoride. This is known as fluoride abstraction, and this forms a beta silicon stabilized carbocation, and which is highly reactive. After that, the carbocation reacts with a hydrocarbon through CH insertion forming a carbon-carbon bond and forms a beta-stabilized uranium. Finally, the uranium ion loses a proton, allowing the catalytic cycle to repeat the whole process over again.
For synthesizing substrates, there are three major steps that we go through. The first is setting up the reaction, and then we work it up and do extraction, and then lastly, there's purification and characterization. So for setting up the reaction, we need to run reactions in the right conditions. And some of the ways that we do this is in the fume hood, which is that one. And it basically captures and exhausts harmful fumes, vapors, and fine matters, or things that are definitely not good to breathe in, to make sure you're okay. And some examples of this are silica gel and residue from previous reactions. And for reactions that are air and moisture sensitive, we use the strength line, which is that one. And it creates an environment of inert gas like hydrogen or argon, or if you want nothing at all, vacuum. And in order to run reactions, this is the step where we're mixing our different chemicals together and actually having the chemical reaction take place. So we need specific chemical glassware. So your pick, whichever one fits with your reaction works. And then we use a scale to measure out what chemicals we need.
Okay, so this is basically the glove box, and this is where we work with air or moisture sensitive chemicals. So it's similar to the Schlenkline, but it contains many more chemicals. And instead of normal air, the glove box is filled with inert gases such as argon or nitrogen, which creates an environment with almost no air or moisture. After completing the reaction, we separate our desired product from volatile reagents by products and solvents. So basically this over here is a separatory funnel, and it's used to separate two liquids that don't mix together, which creates an organic layer and an aqueous layer. These layers are formed because the liquids have different densities, and this allows chemists to collect the two layers separately. And this over here is brine, which is a salt water mixture, and it's good to use after the separatory funnel because it uses equilibrium to draw out the remaining water from the organic layer to dilute the brine. And this is sodium sulfate, which also helps with water removal because it clumps up the below water. And this is the rotary evaporator, or for short, rotovap. And this basically removes volatile solvents from a solution under reduced pressure. This allows the solvent to evaporate at lower temperatures, leaving just the product behind. Lastly, this is our true product, which is the mostly desired compound, but it's not quite pure yet, so
we need to purify it. So one way that we use to purify our crude material is using column chromatography, which is that one. And it's a purification process to get the compound you want without impurities. So you see there are different layers to this. There's like an orange layer, and there's a yellow layer, and they're separated by the polarity and the gravity, or sometimes we use pressure to run your solvent through the column, and that's how we separate out the impurities from the compound you actually want. And after you get your product, you have to see if you actually got the product that you want. Maybe you didn't make it. So one way that we test this is to use a NMR machine. And an NMR machine is a tool we use to determine the structure of a molecule. And the most common NMR to do is a proton NMR, which is a snapshot of all the protons in your molecule. So this is a NMR sample with your product inside, and we put it in this NMR machine, and it scans it. And after you scan it, it gives you a spectrum like this, which shows different types of peak, and it gives you information on where each molecule is in the structure and how, what bonds do they make. This right here is TLC, which we use to see if our product is coming out of the column. And to see it, we're using a plate. Sometimes we can't see our product with the human eye, so it's UV light sensitive. So we use a UV light to shine on this plate to see if our product's on there. This is one of the reactions that I ran during my time in the lab, and it yielded a 72.2% product yield. And I took it to the NMR machine, and this is my spectrum that I got. As you can see, there are two peaks around like the 7.5 and 8, and these correspond to the bonds here. And there are only two H bonds here because there is a line of symmetry right here. So this bond and this bond is the same, they're equivalent. And this bond is also the same, they're equivalent. So each peak here corresponds to two bonds. And so it makes 4 total protons. And this small baby peak corresponds to this hydrogen, which is not shown between the two methyl groups. And then this big gigantic spike on the right corresponds to these two methyl groups. Methyl groups are CH3, so they have 3 protons each, and if you have 2 of them, you have 6 protons. So this peak corresponds to 6 protons. This is a second reaction that I ran. I just ran this, so I don't have the yield yet. But one thing to point out is the product of my first reaction I used as starting material for the second reaction. And this is an example where we use more simpler molecules to make them more complex. And then we use the complex molecules to make things more complex. So, yeah.
And these are one of the 2 reactions I ran. So it had a 24.6% yield. And over here, if you see the TBU, so TBU basically stands for 3 methyl groups. And if you can see that there are 2 TBUs, which basically means that there's 6 methyl groups. And each methyl group basically has 3 protons. So that's 18 protons in total. And that corresponds to this large peak, which has an integration of basically 18. And to the left, you also have these like 3 separate tiny peaks, one each corresponding to like 2, 2, 2. And they all relate to these like hydrogen bonds that are at each corner, but they're not shown because that would make our diagram much more messier. And there's also another peak of 2, which corresponds to this double carbon bond. So basically carbon bonds to 4 separate things. So that's where so we assume that there will be 2 potential hydrogen bonds over there. And this is the second reaction I ran, and it had a 47.2% yield, and there is a big spike on the right of 12. This is caused by the 4 methyl groups here, here, and here. And then over here, there's a small peak of 2, basically, and that was caused by the carbon bonds, which are once again not shown, one here and one over there. And that is the end of our presentation. Lastly, we would like to thank Mr. Mitch and Angel for the opportunity.
Thank you. Any questions?
So you were working in an actual lab, so you got some lab skills. What was the process like in learning the different processes that you were able to use in order to do your research?
Well, while Angel did send us some videos, he was more of a hands-on person. So he would like show us how to do the beginning process, and then we would repeat after him, basically. Most of the times we had like morning and evening schedules. So she would begin a column, for example, and I would like end the column.
Yeah, so when I first started, I had absolutely no idea what a column was or how to run a TLC plate, but as summer went on, I learned a little bit every day. And then from the beginning where I didn't know how to do anything, now I can run a column by myself unsupervised and making probably close to 0 mistakes, so that's good. In chemistry, you don't want to make mistakes. Yeah.
Do either of you want to pursue chemistry? You feel like what you learned this summer is driving you to continue with that?
I think so. Chemistry I think it's really interesting, and it intersects with a lot of of their science.
Organic chemistry has been really fun for me, but I'm also like really interested in math, so I wouldn't pursue just organic chemistry, maybe something like chemical engineering. So I can combine what I do things that I like. Okay.
Any other questions? Okay, thank you.